J'aurais bien aimé, hein. C'est pour ce soir la tireuse.
Ouais, d'accord.
The jury has given me the honor to be the president of the jury. We have a few external members. My name is Ramesh Majani. I'm a professor at the University of Minnesota in the US. we have two reviewers, Patricia Degré from Telecom Paris, and Patrick Brenner from KU Leuven. And then we have Doug Smith from Austin, Texas, and Fran from University of Lille. And local, we have Eric Gerham. And Irv Lapwood, and Jan Van, and supervisors, Natalie and Bill Kemper, and Eric Francois. And you're invited to present your work for approximately 45 minutes. Thank you.
Thank you very much, Mr. President. So I'm very happy to be here to introduce you to my PhD work, which is entitled Study and Implementation of a Pré-distorsion Method for Power Amplifiers using Walsh Sequentielle Modeling. This work was supervised by Dr. François Rivet and Professor Étude. My presentation will be divided into 4 parts. First, I will do a general introduction about digital pré-distortion for 5G power amplifiers. Then I will detail my first contribution to this topic, which is a Walsh-based digital pré-distortion. Following, I will highlight the architecture and implementation of an analog Walsh platform in an integrated circuit. And finally, I will draw some conclusion and perspective about this work. So first, let's start with a bit of history about mobile networks. In the 1980s, the first generation of mobile networks introduced voice communication with mobile devices. In the 90s, 2G was exploding. The year 2000 saw 3G enabling internet access with mobile devices. 4G democratized multimedia access on mobile devices. And nowadays, with 5G, so let's see what's new. 5G can be divided into 3 main topics. The first one is an ultra-reliable, low-latency communication with applications like autonomous car or remote surgery. The second one is a massive machine-type communications with applications like connected agriculture or smart cities. And the last one is called enhanced mobile broadband, and its goal is to face the exponential growth of data traffic. And this is the context of my study. So here on the right, you have a graph by Ericsson. On this graph, there is a forecast of the global data exchange for the coming years, and we can clearly see this exponential growth. So how can 5G respond to this? First, with higher data rates, effectively multiplying by 20 the current data rates for 4G, and then with a wider coverage, so more device density and wider frequency bands. So now let's see how those frequency bands are used during a communication. So let's say you are a user of the mobile networks and you want to access the communication networks. So your smartphone will be called a user equipment, and you will first need to communicate with a device called a base station. So we'll communicate with this base station on an uplink communication. So 5G has a dedicated frequency band for this communication. Then the base station will access the communication network that will send data back, and the base station will have a downlink communication with you, send you back your data, and there are frequency band dedicated for the downlink communication. So it's also important to say that there are different technical specifications for the smartphone and the base station. Now, if we look a bit about the 5G frequency band, it can be divided into 3 main parts: the low band, the mid band, and the high band. Now, let's say you are in outdoors and you want to have a communication. If you are in a long distance from the base station, you will communicate with a low band base station. So you will have long range communication, but a very low number of users that can access this base station, and you will have low data rates. If you are in the mid-range distance, you will have the mid-band communication with higher density of users and higher data rates. And finally, in a very short-range communication, you will communicate with a high-band base station with a very high capacity of users and short distance, but very high data rates. And it's not yet deployed in the site. So now let's focus on what's inside the base station and the smartphone. So in those devices, you have a system called an IQ transmitter. So on the left, you will have your data that you want to send. So it can be a voice message, internet information. It will be then converted to an electrical signal with digital to analog converters. This signal will be up-converted to a frequency band that I showed just earlier. This signal will be amplified by a power amplifier to give strength, and then it will be radiated by an antenna to a complementary architecture, which is called a receiver. And in this receiver, you will have the same operation, but in the other order to retrieve your data at the end. So now if you combine the transmitter and the receiver, you will end up with a transceiver. Transceiver have many constraints, so here it's a small list of constraints, but one of the main constraints is the power consumption of the receiver. Every component of the transceiver consumes power. So now let's see a quick power breakdown of a transmitter for a transceiver for a base station. So to generate all the DC voltage, you will have 40% of the total energy consumption. For the digital part, which is the baseband, radio, and the digital signal processing, you will have 13%. For the radio frequency front end without the power amplifier, you will have around 6% of the total power consumption. And the rest is power amplifier with more than half of the power consumption. So here we can see that for a base station, it's really a critical device. So now let's go into the trade-off and the characteristic of a power amplifier. So as I said earlier, a power amplifier is here to give power to your input signal. And it has a very particular characteristic, which is called the AM/AM characteristic. It can be divided into three main areas. The first one is the linear state. The output is a linear amplification of the input by a linear power gain. Then as the input power increases, you will enter a compression state where the gain is no longer a constant. And it's often characterized by the 1 dB compression point. And then as the input power increases, you will end up in a saturation area where the output power is constant, whatever the input power, and it's called the saturation power. Also for the phase, you will have similar characteristic with a constant phase modular an angle, and you will have non-constant phase for compression and saturation. So now let's go back to the AM/AM curve. If you are in the compression or saturation state, you will end up with distortions in your signal. But before talking about distortion, I first need to introduce a very important metric of 5G signal, of a global signal, which is its peak to average power ratio, and it's defined by the ratio between the maximum instantaneous power of your signal and its average value. So let's see an example. For example, if you have a continuous wave, IQ continuous wave signal, you will end up with a 0 dB peak to average power ratio. It means that the maximum power of your signal is equal to its average power. Now, if you send this signal to your power amplifier, it will result in a single point in the AM/AM characteristic. And now, if we take 5G signals that has, for example, 10 dB peak to average power ratio, so we can see on the left the peak power of this signal, you will have a dynamic of power inside your amplifier, and it means that if you are in the linear state, you might have, in average, you might have some levels that will go in the compression state, and we will have distortions. So now, and also, 5G uses a very complex technique that ends up with high peak to average power ratio signals like WaveDM or carrier aggregation. So now let's see the distortions generated by a power amplifier. So in this slide, I will move the average power of a modulated signal along the AMA curve, and we will see the distortion on the output spectrum and the constellation of your signal. So here I move the average power, and we can see first distortion is the pollution of adjacent channel of your communication. So it means that you will pollute users around you, and this pollution can be evaluated with a metric called the adjacent channel power ratio. And as you move up to the saturation area, you will also pollute more than just the adjacent channel. And now a second distortion is degradation of your constellation. So here we can see that we'll have a phase shift of our constellation, and we'll have a noisy constellation. Therefore, in the receiver, it will be more difficult to retrieve your data. So that's for the nonlinearity. Also, there is a second distortion in power amplifier, which is called the memory effect. So as we know, power amplifiers are composed of passive and active components, which are frequency dependent. Therefore, our power amplifier will be frequency dependent, and this frequency dependency will be called high frequency memory effect. Also, since we have an active device, it will generate heat in our circuit, and this heat will change the behavior of the power amplifier, and it will end up with another memory effect, which is called the low frequency memory effect. So now here we will see how can we see a memory effect in an AMAM curve. For this example, it will be a high frequency memory effect. So here we have the AMAM curve of a 5G signal, 5 megahertz bandwidth. As we increase the bandwidth here up to 20 megahertz, we'll see that the AMAM curve has a dispersion along the linear curve. And as we increase even more the bandwidth, we'll see a very strong memory effect. And this memory effect will introduce asymmetrical adjacent pollutions, and it will be even harder to demodulate at the end. So now we've seen that where we are in the linear, we don't have distortion. Where we are in compression or saturation, we have distortion. So maybe we can say, okay, let's go into the linear state to don't have to deal with distortions. But if you are in the linear state, you will end up with lower output power with your power amplifier, so it will be more constrained on the receiver. And if you look at the efficiency of your power amplifier, it's much higher in the compression and saturation states compared to the linear state. So is there any solution to this trade-off? One solution might be to make the pair operate in its compression area for efficiency, and then we will use linearization technique to reduce the distortion. And in my PhD, this linearization technique is called digital pré-distortion. So now I will explain the different principles of digital pré-distortion. So to do that, I like to do an analogy with optics. So let's say you have myopia, and so you can't see in the distance. So to compensate for this distortion, you will put correct lens in front of your eyes to correct the distortion of your eyes. It's exactly the same principle with digital pré-distortion. We have our power amplifier with its distortion, and we'll put in front of the power amplifier a device called a pré-distorter that will have an inverse behavior of the power amplifier to compensate for irregularity, and the overall chain will result in a linear power amplifier. And also it's important to say that DPD changes the signal and not the power amplifier. And like lens, it has performances and a cost. So now let's see the implementation of digital pré-distortion in a transmitter. So here you have our conventional transmitter. I will just simplify the schematic. And so here you have your nonlinear power amplifier. To do digital pré-distortion, you will need first to sense for the nonlinearities of your power amplifier. So you will need a coupler to have a copy of your output signal. And this signal will be down converted to digital to compute this inverse model. And it's divided into two steps. First, we need to evaluate this inverse model, and then we will apply it to our original signal, and the overall chain will result in a linearized power amplifier. And so now let's see what are the mathematics behind digital pré-distortion, first with the different models. So we've seen that a power amplifier is nonlinear and has memory effect. Therefore, our inverse model needs to have this nonlinearity and memory effect. A very famous mathematical theory that can model this is the Volterra series, with its coefficients of the inverse model and the Volterra waveform. Here we can see the nonlinearity with the polynomials and the memory effect with the different delays of our input signal. But as we can see, these sums are infinite, therefore we cannot implement them in digital. That's why we need to truncate this model with a very famous model, which is called the memory polynomial. So here we can also see clearly the linearity with the polynomials and the memory effect with the multiple delays of our input signal. It has q times n coefficient, but this can be reduced to half using only odd power for the polynomials. It can be also written in a vectorial form, which is composed of the memory polynomial waveforms of our input signal and the pré-distortion coefficient of the DPD. So we know our input signal, but at first we don't know the pré-distortion coefficients since we don't know the inverse behavior of the power amplifier. So as I said, this inverse model is unknown at first, and it might be dynamic because power amplifiers are power, frequency, and temperature dependent. So to evaluate this model, we can use a process called adaptive filtering to search for this inverse model. So basically, an adaptive filtering is composed of an adaptive filter and an adaptive algorithm. An adaptive filter is a filter that has its coefficient that change over time. Here you have the equations of the and they are updated by an adaptive algorithm that update the filter in order to reduce the error between the output of the filter and a reference signal. So very famous equations, updating equations are the least least square equation, normalized least least square, or recursive least square. So let's say if you want to build a model of your power amplifier, you will use the input as X and the output as D. But now, if we want to compute an inverse model of our power amplifier, we will use the output as X and the input as D. So now we see how to do digital pré-distortion. Let's see the different key performance indicators of such digital pré-distortion. So first, we have the speed, how fast your algorithm can converge to a static solution. The accuracy, so how accurate is this inverse model. The robustness, so is this algorithm stable and accurate under noisy environment? And finally, we have the power consumption of the DPD, and it's often omitted in the literature, but it's very important since if the power consumption of the DPD is superior to the one of the power amplifier, there is no point to do a digital pré-distortion. So we can do a coarse estimation of the power consumption with the following formula, which means the number of floating point operation of your algorithm with the energy efficiency of your target. It can be a CPU, GPU, or ASIC. And we calculate the number of floating point operation with the following metrics. So now I've drawn a global picture about digital pré-distortion. And the objective of my PhD is to develop digital pré-distortion with high performances at a low computational cost for the 5G standard. This DPD must be compatible with our targeted architecture, which is a Walsh-based architecture. And this architecture is used in two projects. So the first one is a 5G project, a national project, and the second one is a sub-terahertz project, which is a European project. So I did two contributions to this transmitter. The first one is a Walsh-based digital pré-distortion, and the second one is an analog Walsh transform in the feedback path. So now let's go into the mathematics behind the Walsh-based digital pré-distortions. But before, let's talk about some Walsh mathematics. So the Walsh functions were introduced and invented by Joseph Walsh. There is their mathematical description, but I will not detail those equations. And we can just say that those functions are square waves that takes value between +1 and -1. They can be implemented in digital as a discrete matrix here with a different Walsh function. But a very famous implementation is this recursive formula, and we end up with an order of the function called the Adama order. Also, there is a third order, which is called the séquentielle order. And basically, sequency is like frequency for Fourier, but here it's for Walsh. And it corresponds to the number of sign change inside a function. So this function form an orthogonal basis. So we can decompose any signal into this set with the Walsh series decomposition. It is written here in scalar or vectorial form. And in the vectorial form, we have the Walsh coefficients. So it's the representation of our signal in the Walsh domain. And we have the Walsh function after. So this is the principle that was used yesterday by Pierre to generate an RF signal. So to compute the Walsh coefficient, you will need to perform a Walsh transform of your input data. This Walsh transform is only composed of additions and subtraction, and its computational complexity can be reduced to n log the n with fast. So now we see the Walsh mathematics. Let's see how can we use it with digital pré-distortion. We saw that digital pré-distortion is an adaptive filtering process. So now, how can we do filtering in Walsh? So we know that filtering is a convolution in time domain. We can write it as a matrix multiplication. Now let's see how can we do it in Walsh. So we know how to compute the input and output Walsh coefficients of our system, and we know that the inverse Walsh transform is like the Walsh transform divided by n. So let's first multiply the first equation by the Walsh matrix. So we have this equation, and here we want to make appear the input and output Walsh coefficients of our system. So here, uppercase y and uppercase x. And here we can just see that we can link the input Walsh coefficient of our system with the output through a filtering matrix in the Walsh domain. So now we know how to do a filtering in Walsh. And this matrix has a very interesting structure, which has a lot of zeros in it. So it's called a block diagonal matrix. So now we see how to do filtering. And if we want to recall something from this slide, it's those equations. But now how can we do a memory polynomial filtering in the Walsh matrix? So we saw earlier that for digital pré-distortion, we need a memory polynomial. It can be written as the following equation and in vectorial format. Don't worry, I will go into a deep translation of those equations in Walsh, but we can just clearly highlight two interesting properties, is that we can do this filtering in the Walsh domain using a power property which involves the dyadic convolution between our input Walsh coefficient, and we can build the memory time of the memory polynomial with time-shifting matrix. So now we've seen how to do a memory polynomial. Now let's make it adaptive to compute the inverse model of the power amplifier. So I showed earlier some equation about a scalar least mean square. We can do it in a vectorial format. And again, I will not show you a deep description to go from this to the Walsh, but we can also perform this block updating in the Walsh domain using the matrix I showed you just earlier. So this is my first contribution to this work, which is a Walsh-based mean space square for digital distortion, and it was the subject of IEEE journal. And so in those equations, those matrices are block diagonal, therefore we have a reduced complexity and reduced power consumption, and we are using a block approach, therefore we have a high speed for this computation. So now we've seen how to do the digital distortion in the Walsh domain. Now let's do some simulation and measurement to see how it performs. So we want to evaluate this algorithm on the different KPI I showed earlier, so accuracy, speed, robustness, and power consumption. We want to compare our algorithm with a conventional DPD algorithm, which I introduced earlier. For the speed, accuracy, and robustness, we will look at the normalized mean square error between our linearized output and the original output to the power amplifier. And we can look at it over the iteration to see how fast this algorithm can converge to a more or less static solution. We can also, for the accuracy, look at the ACPR, which is a famous metric for the 5G, and the EVM also, as I introduced earlier. For the power consumption, we'll use the following formula that I introduced also earlier. And for the energy efficiency, we'll take this value, which is 15 teraflops per watt, and it corresponds to the energy efficiency of a target that we found in the literature. So now we've seen what we want to evaluate, but how can we simulate digital pré-distortion on an integrated circuit before measurements? So on one side, you have a high-level programming language with Python or MATLAB. So you will need communication toolbox for 5G and signal processing for DPD. And on the other side of the wall, you will have CAD software like Cadence or IDS to design your power amplifier. So this power amplifier can be an ideal power amplifier or post-layout simulation. And in those software, we can use a simulation called envelope transient, which involves a transient simulation of modulated signal. So now let's see if so now we found a solution to bridge this gap. So first, a solution with the available resources at the IMS lab. So we have the Mac and PAC co-simulation workflow, which involves MATLAB, ADS, and Cadence. And on the other side, we also tried an industrial solution, which is called Vision. And if you look at the simulation time and the accuracy of our model in those different co-simulation, if we would like to do a full envelope transient on, for example, a sub-terahertz post-layout simulation of power amplifier, we have 525 hours of simulation, whereas with this workflow, we have 47 minutes and an error of 6%. And with the industrial solution, we have 6 minutes of simulation and 1% error. So this was the subject of a paper that was presented in September in a European microweek. So now let's see the architecture that we want to simulate. So here we have our DPD architecture. The power amplifier we want to linearize is a 5G power amplifier that has a wideband characteristic, and it is the PhD of our colleague Rémi Kay. And also during my work, I was able to do some digital pré-distortion on a sub-terahertz power amplifier, which is the PhD of Antoine Lomel. So now let's go to the results of our simulation. First, we have a narrowband FR1 signal, so 20 megahertz signal, 16 QAM constellation. We use also phase factor reduction. So we have 2 phases for the simulation. First, the learning phase. So we use the parameter of the MP model to find the best inverse model for the power amplifier. So we do this over 20,000 data, and we iterate this process 5 times. So here we have a normalized mean square for each algorithm for each parameter sweep. We can define 3 areas. The first one is underfit model, where there are not enough coefficients to model the inverse of the power amplifier. The second one is overfit, where we have too many coefficients. And finally, for each algorithm, we find a minimum of this value, which corresponds to the best fit. So it's an ideal number of coefficients to model the inverse behavior of the power amplifier. Also, if we look at the power consumption, we see that the recursive least square has a much higher power consumption than the 3 other, but I will go into much detail in the following slide. So now we found our best model, which is Q equals 7 and M equals 1. Let's apply it to one subframe of 5G signal and evaluate the different KPIs for each algorithm. So in terms of speed, we look at the number of iterations required to reach normalized mean square error below minus 40 dB. So here we see that our algorithm is the second best in speed. In terms of accuracy, we can look at the normalized mean square error between the linear output and the input. So we want this value to be as much low as possible. And here we can see that we can achieve the same accuracy as other algorithms. And here we can clearly see the linear speed of the power amplifier. Now, if you look at more metrics that are more linked to 5G, we can look at the ACPR, and we see that we are able to reduce by 20 dB, to improve by 20 dB the ACPR and by 4% the EVM. And now what our algorithm truly shines is in terms of power consumption. So here we can see that we have 10 times less power consumption than the RLS with the same performances. So now we see the behavior of this algorithm on a narrowband signal. So it has the same power consumption as the least mean square with the accuracy of the recursive least square, and there's also a better speed than the normalized least mean square. So now let's see the simulation with wideband FR1 signal. So we did first a learning phase, and we found that these are the best coefficients for our inverse model. And we evaluate also the different KPIs. And again, we have the same conclusion. We have the second best in speed, and we have very good accuracy for this model. We're able also to reduce by more than 20 dB the ACPR, 5% the EVM. And again, our power consumption is much lower than the recursive least square, but this algorithm is much faster than our algorithm. So we see that we have the same behavior of the wideband signal. So now let's go into measurement to see how it behaves in a noisy environment. So the pair we want to linearize is the same power amplifier, but it was manufactured. So it's a picture of this power amplifier. So this is our measurement setup. So first we have a USAP-based measurement setup. So in an USAP, you will have an FPGA and an RF front end. So it can go up to an instantaneous bandwidth of 160 megahertz. Its frequency range is up to 6 gigahertz, and the data is quantized on 14 bits. We use parameter and coupler to sense for the input and output power and signal of the power amplifier, and we use attenuators to protect our devices. So the DPD is performed in MATLAB, and I also developed a graphical user interface to help do the DPD to make it more easy to use. And this is a photograph of the setup, which is in the NanoCode platform of the IMS laboratory. So now let's see the results. So we did this measurement on the 50 megahertz signal. And we found that the base model is Q equals 5 and M equals 3. And we applied this model for each algorithm on the full 5G frame, which lasts 10 milliseconds. And here we can see the same conclusion as in the simulation. And for speed, we see that we are here best in speed because we were forced to limit the speed of this algorithm because otherwise it would have divergence and it couldn't find any model. So again, in accuracy, we can match this algorithm. And here, again, in power consumption, we are more than 20 times less than the recursive least square. So we see that the performance has been assessed in measurement on an integrated circuit. So during this part, I showed you a Walsh-based block LMS to estimate a memory polynomial in the Walsh domain. It has a reduced complexity, so 10 times less than the recursive least square. Enhanced speed with a block updating, so 10 times more than the LMS and superior to the NLMS. A good accuracy in a noisy environment. And this performance were assessed in simulation and measurement on narrowband and wideband 5G signals. So now can we go even further in the integration of a Walsh DPD in a Walsh transmitter? And so we can do it by taking the Walsh transform in the algorithm to the analog domain to pre-compute the Walsh coefficient of our signal. So now let's see this implementation on an integrated circuit. So for the proof of concept, we have another 3 Walsh transform, which involves 8 Walsh coefficient. For the frequencies of operation, we want to be the baseband of 5G, and the maximum bandwidth of the 5G signal is 200 megahertz. This is the sample rate, and since we need to sample the nonlinearity, so the spectral regrosses of our signal, we need to oversample our signal. So we have a 1.22 gigasample per second sample rate. So this is the first architecture, and here you have the analog Walsh transform with, as an input clock, 1.25 gigahertz. But we want also to assess its performances on the RF sampling, so we can go up to 10 gigasample per second to sample the 5G FR1 bandwidth. In terms of levels, we know that the saturation power of the power amplifier is 22 dBm. After the copper is -8, and it corresponds to a peak voltage of 115 25 millivolts. This has been implemented in 28 nanometer FDSOI CMOS technology from ST Microelectronics, which has a high frequency which can operate at high frequency, and it is very low power with a minimal size inverter. We have around 28 microwatts with a clock at 1.25 gigahertz. So now let's see for the operation we want to implement in the analog domain. So we know that the Walsh transform is only composed of additions and subtraction. So here we have another 2. The fast Walsh transform can be used to reduce this complexity with a radix structure here. So in this structure, we can compose into several smaller structures. So in the first stage, we have 4 order 1 Walsh transform. In the second one, we have 2 order 2 Walsh transform. And in the final stage, we have our order 3 Walsh transform. So we see that in those structures, we have a standard cell called a radix 2. And so how can we perform this standard cell in the analog domain with analog components? So to do this operation, so the inputs are A and B, and we want for the outputs the sum and the difference of those inputs. To get those inputs, we will need a time interleave track and hold to get the discrete level. To do the sum, we use a charging circuit, and this circuit was involved in the work of Dr. Sadhu and Professor Arjani, in which they were performing a Fourier transform with an analog in the analog domain. And to do the difference, we need to work with differential signal to have the minus sign. So now we see that we need digital circuit to generate the clocks, to activate the switches, and we need some analog circuits, so the switches to perform the operation. So now let's see the architecture of the circuits. So first, we have our time interleave track and hold here. So we have our input signal that goes into the different paths. Those switches are activated with 8 multi-phase blocks, which are generated by our main clock generator, and they are generated from our input signal. Then following our first stage of radix operation from the order 3 Walsh transform, and also those are activated by 3 clocks. And following, we have a demultiplexer and active balance to go from differential to single-ended for measurement purposes. So actually, we added a demultiplexer because we decided to double this architecture. So I decided to double the architecture since when the capacitors are shared between the track and hold and the radix. Therefore, when the radix operates, new data samples are not required. Therefore, we need a second architecture to sample for the data while the first one does the transform. And once it's finished, this one samples and the other one does the transform. And we can select the output with the demultiplexer. So now let's go into just a standard component of this circuit, which is a cross-differential CMOS switch. So with the CMOS structure and the backgate of this technology, we have a very low resistance on a wide dynamic range. And thanks to this leakage cancel transistor, we have a very good isolation when the switch is off. So here you have the layout of this switch, and this switch is used for the time interleave track and hold, the radix, and the demultiplexer. So now let's see operation in transient simulation. So here we have our two CMOS switch with the two discrete level A and B. So here we have the tracking phase and the holding phase. And once the two signals are holded, we activate the third switch to have a mutualization of the charges along four capacitors. Therefore, we will end the sum of our two input signals. For the difference, we just need to invert two wires in this switch. So now let's see a transient simulation of this circuit. So here we have our different tracking phase and holding phase for the different levels. So we can see this sampling, and then after we have the sharing phase where we perform the order 3 Walsh transform by activating the different switch to mutualize those charges. And once it's finished, we go back to sampling. So here we can clearly see, if we zoom on the sharing phase, the three activations for the order 3 Walsh transform. So here we have 4 order 1 Walsh transform, 2 order 2 Walsh transform, and 1 order 3 Walsh transform. So if we look at the Walsh coefficients computed by this circuit here, compared to an ideal Walsh transform on the discrete level, we have a normalized mean square error between the levels by minus 18 dB. So now that's for the simulation. Here you have a complete layout of the chip. So here is its size. So first we have our clock buffer here and the main clock generator. We decided to for access to inside the circuit. Moving on, we have our distributive tree and our different track and hold switch. And here we have a capacitor link. Moving on, we have our radix structure here with the three stages, and as we see, it's double for the two architecture. Here we have our demultiplexer to choose between the first architecture and the second, and finally we have our active balance to go from differential to single-ended. So here's a photograph of the chip manufacturer. We use a test PCB to measure this chip, and we use a socket for rapid testing. We use also regulator, decoupling, and potentiometers to adjust the biasing. And this circuit is put in our measurement setup, which involves continuous wave generator for the input signal and the input clock. And those signals are controlled by a GPEB communication to do some sweep analysis on this circuit. For the output, we use a scope which has a very high speed, up to 40 gigasamples per second. And we have 4 channels on this scope, but actually we have 8 output to measure. Therefore, we need to separate our merger into 3 phases. The first one, where we sample the input and the first 3 Walsh coefficient. Second one, the following 3 coefficients. And finally, our last 2 coefficients. So here you have a photograph of this setup with the continuous wave generator, our PCB socket, and the IC inside. And here you have the scope. So before going to the measurement of the analog Walsh transform, I did an initial measure to verify the functionality of the digital part and the power consumption of the circuit, since the only contributor to this power consumption is the digital. So I measure one of the time interleave clock to verify its behavior. So it has a clock frequency same as input divided by 16 and a 25% duty cycle. At first, I wanted to measure it on high impedance, but due to parallel capacitance of the scope, we had a filtering of the clock. Therefore, I had to do measurement on the 50 ohm. So here you have this clock generated in the circuit. So we can clearly see the 25% duty cycle, and it has 72.5 megahertz. Input clock is 72.5 megahertz. Here we go higher in frequency. Here we have an input clock 1.25 gigahertz. So if we take a look, we can zoom and we can clearly see the behavior, and we were able to go up to 5 gigahertz input clock, and we can clearly see the behavior of the digital. We also measured this duty cycle over the bandwidth, and we are in around the 25% duty cycle. Now for the power consumption, we have a very good correlation between the measurement and the simulation, since we know that from the power amplifier that were manufactured in the same wafer, that this wafer has a fast corner, and therefore that's why our measured power consumption is lower than the simulated in typical. So now we've seen the behavior of the digital. Let's see the behavior of the analog transform. So first, with low frequency to verify its behavior. So here we have our different, so the input signal and the different output signal. So we can clearly see the sampling phase, sample hold, and the different sharing phase. If we zoom on the sharing phase, we can clearly see the order 1, order 2, and order 2 Walsh transform. But actually, if we look at the amplitudes, we have some mismatch in the active values of the circuit. That's why we have some difference here, because we have a gain imbalance and a different DC of states at the output. So we will need to embed to find this contribution to compute the Walsh coefficients. And we still also measured with higher frequency clock, so 1.25 gigahertz. And again, we can clearly see the sampling sharing phase. But as we can see, the signals are very noisy, and this circuit needs improvements. Also, I did many measurements with multiple amplitude and phase to verify the impact on the Walsh coefficients. And both architectures, or A and B, were verified individually. But we will need to enhance this bench to perform a continuous time sampling. So that's for the measurements. So to conclude on this part, I showed you the concept and implementation of an analog Walsh transform in an integrated circuit. It's a switch-based architecture which is controlled by a multi-phase clock. And we were able to showcase in simulation continuous time sampling with a doubling of the architecture. The performance of the digital and the power consumption were assessed in simulations and measurements up to 5 gigahertz clock. And the behavior of the analog Walsh transform is clearly highlighted with early measurement results. But we need to improve the layout and some circuit to have better results. For example, we can try to have more compact layouts, reduce the switch size, and also work on the interconnections that are very long in this circuit. So now to conclude on our work that I showed, so about introduction, the DPD and the Walsh transform. So first for the DPD, I showed you some context about DPD for 5G power amplifier and the trade-off between linearity and efficiency of the power amplifier. Also the different models involved in DPD and the different key performance indicators. Then I highlighted my first contribution to this topic, which is Walsh-based mean speed square for digital pré-distortion that showed a low computational complexity, high speed accuracy that was assessed in simulation and measurement, and this algorithm matched Walsh-based transceiver. My second contribution is the analog Walsh transform in an integrated circuit with some analog signal processing with charge-sharing circuit. This proof of concept was validated in simulation and measurement, and it could be even lower power and higher frequency with some layout optimization. And finally, I did a complementary contribution to this PhD, which is a co-simulation workflow for DPD on an IC before measurements of the power amplifier, and a USCP-based digital pré-distortion bench to do some fast testing of your DPD. So now for the perspective about DPD, we could try to go even beyond high-level automation with an hardware implementation to verify the power consumption in a target. We could also try to have a more complex model that can model more complex phenomena in the power amplifier. We could also try to take those models and put them in the Walsh basis to compute those models with the input and output Walsh coefficient of the power amplifier. Also, I did a big contribution about the conception of a full Walsh transceiver. So I couldn't show it during this presentation, but it uses some Hilbert filtering for image rejection And with some partners, we have some AI involved in this transceiver. And finally, for the circuit, so we try to improve the circuit with some circuit and layout optimization. And maybe an idea to go even beyond is to perform Walsh filtering in the analog domain, since we saw that we can do Walsh filtering. And maybe it could be used in the receiver, for example, to filter the blockers as an example. Now for the last perspective, which are the simulation and measurement tools, we could try to enhance our co-simulation workflow. And an idea that we had is to do a DPD during the power amplifier design, and maybe you can reduce the linearity constraint during the design, knowing on how much there will be the distortion will be compensated in measurements. And finally, it will be also great to improve our digital pre-distortion bench and to make those co-simulation and bench open access. So this is the scientific contribution of my work. So we have an internet journal, which is an IEEE Transaction and Communication. I also showed my work during 2 international conferences, 3 national conferences, and my work has been patented 2 times, so 2 French patents, and I co-authored 5 papers, so 4 with colleagues Rémi Kay and Antoine Lomel, and 1 with a partner from Cairo. Thank you for your attention, and I will be glad to answer your question.
Thank you, ma'am. Now I'd like to open the questions for the reviewers. Patricia, you go first.
Okay, thank you. Thank you very much, Mr. President. First of all, I'd like to thank Nathalie and François for inviting me for this PhD because it's always a pleasure to come in Bordeaux, and I really appreciate your work. I read the manuscript, it was really clear, very interesting. You did a lot of work, and so I put everything in my report. But concerning the presentation, I appreciate the presentation, clear and dynamic, which underlines the realizations of your PhD. The introduction was really nice, didactic, very nice, and very well illustrated too. And then we spent 20 minutes on the paper, so then it was very fast.
Yes.
But, okay. So I'm looking for people discovering. Okay, so I have some questions. First of all, your first study was the comparison of the LMS, LMS, RLS, WLS. So you start slide 29 for the different KPI.
29. Or do you want the different KPIs? Maybe I can hear.
Yeah, I have a first question on the algorithm variables.
Yes.
Because you said, okay, there were 5 items, and it optimized conversion speed while avoiding instability.
Yes.
But I was wondering how sensitive is the algorithm to these parameters? That is there a wide range of good values, or limited few restricted values to that as well?
Okay. Maybe I can. Maybe I will compare with a very conventional algorithm. So you can see that on the Limit square, for example, you have this parameter which involves which links the speed of your algorithm. So as you increase your algorithm, you go even faster. But actually, there is a limitation which is equal, if I remember well, to 2 divided by the trace of the regressor, the matrix of the regressor. So actually, we have a maximum limit for this value, And after that, we cannot assure that this algorithm will not diverge. So we have, so if we have zero, we have to update this coefficient, but we have a maximum value for this. And we have the same for the NLMS and the RLS, and also here for the RLS, if it's inferior to 1, it might diverge, and that's why in our simulation it was 0.99, so to make it just go very fast. But in measurement, there were divergence of this RLS algorithm. So this is for the conventional algorithm. Actually, for the Walsh algorithm, we have also a new component, so that has upper limits. Beyond this limit, I cannot assure that this algorithm will converge. And also to avoid some convergence, I actually did normalization of the updating weights like this. So here it's a constant to avoid if this is too small, this will go very high and we'll have a divergence of your algorithm. So I didn't write equations for the Walsh elements to normalize one, but it's in the manuscript. And I didn't do a mathematical approach to see in theory what is the maximum value. I did just with testing of discrete values and to see how fast can it go. And beyond this speed, I stayed with the variables I found. And so in the simulation and the measurements, I increases those variables to have the base speed to really showcase how fast each algorithm is to compare them. I don't know if that answers your question.
Yes, so I understand that you try to be fast.
Yes.
And there's quite a large range of possible values.
Yes.
Thank you. So I have a question about the simulation or the tested case with FL1 PA at 4.5 gigahertz.
Yes.
Slide 31.
Yes. So I think it starts here, but I can go. So these are the different parameters of this parameter. And here we have some the learning phase to find the best model. And after we apply the best model for each algorithm on one subframe of 5G.
So you said so this okay, you try with 2 PA.
Yes.
With a relative bandwidth of 90%.
Yes. So
90%. What does it mean? Because you tested only with 100 megahertz.
yes.
So it's sufficient.
Yeah. So actually, so the 90% is the overall bandwidth of the power amplifier. It goes, so I should know it, but between 2 to 5 gigahertz. It's a very wide band for FR1. And so I only tested 100 megahertz. Since it's wide band, it's not flat along the bandwidth, so therefore you will end up with high frequency memory effect behavior, for example. And so here we can clearly see this for 20 megahertz signal, but with the 100 megahertz, we can clearly see that the gain is not flat along the bandwidth. And this was also measured on the physical power amplifier.
So testing on 100 megahertz is okay for the gain. But it doesn't meet the 5G standard requirements in terms of linearity.
Yes.
EBM, SPS.
Yes.
So my question is this PA had a bad behavior because it was supposed to respect the standard, or was it designed from the start to be used with?
Yeah, so actually, this power amplifier is also involved in the 5G projects, so the Aggregate 5 project. So actually, I started my PhD with the designer of this power amplifier. And so from the beginning, we wanted to do a digital pré-distortion on this power amplifier. And so I'm not going to explain how it behaves, but it has a very particular behavior to have this wideband characteristic. And actually, so we see that to have the best efficiency, we try to go as much as input power as possible. Because if we go too high, we'll end up in the saturation, and we can do anything in saturation, which is physical. We cannot linearize the saturation. But if we have a wide dynamic range in the compression, it's where we have the best efficiency. And so we found that the best input powers, the best efficiency to have a good linearization was this value. And actually, we can see that the AC period doesn't need the 5G requirements. I didn't want them, but for user equipment, so for example, a smartphone, it would be around minus 31 and 32 dB, 33 ACPR. So the requirements are not very high for a smartphone. But if you try to use this algorithm for base station, for example, you have a much more constraint on base station, and you will need to go below 45 dB ACPR for base station. So just to say that in the labs we are the designers designing CMOS power amplifier, and so they are not used in base stations. So this was the power amplifier that I had to test my digital pré-distortion. I don't know if it answers you.
When you compare the power consumption, you compare something that doesn't meet the standards or something that meets the standards. Perhaps you can compare the power consumption of the PR without DPD, but meeting the standards.
Yes. 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 Yes.
It's good for your solution.
Yes. Yes. So I didn't show you, but during measurements, actually we tried to compare. So if I go on the low powers, how much is the efficiency, and if I go even beyond the powers, how much gain I have. And I think that we were able to have at least more than 10% power efficiency for this power amplifier with it was around 10 dB peak to average power ratio, and we had like 9 dB output per cover. So yeah, let's say, yeah, of course, it's important to put this power amplifier in its linear state to see the power consumption and efficiency because maybe it would be sold without the digital pré-distortion.
Thank you very much. Second, I appreciate the mixed code simulation workflow. Okay, it was clear. For me, it's very important because we like to do code design with the team. Just, I have a question on the model. So,
Yes.
Okay. What was the model, the PA model used in simulation? Can you give us details? Because it's unilateral, very low frequency memory.
Yes. So just actually about this workflow to be a bit more precise. So in this workflow that uses this model, at first you need to do harmonic balance simulation in ADS cadence, and in this software they build this behavioral modeling. So it's unilateral because this model was built on 50 ohm input and output impedance. So this is for the unilateral part. And for the high frequency and low frequency memory effects, so for the high frequency, we are just doing one harmonic balance simulation across the bandwidth and the power range. And we give this data to this software. And for the low frequency memory effect, they use two-tone simulation. So we have a first tone that we sweep across the bandwidth and power, and we have a small tone around this first tone that moves all around. And so I didn't go into depth about this mathematics, but this represents the behavior of a low frequency memory effect. And actually, they were showing some results. I think they also have in a UVM macroic on the GAN power amplifier, for example, and they show that their model behaves very well. But I didn't go inside the mathematics. Obviously, there are some polynomial terms inside and memory terms to
At the end, the model is an equation? Or
yes.
Yeah, not
It's purely an equation, and that's why the simulation is very fast.
The order of nonlinearity or the order of...
So yeah, actually, when we compute this model, actually, I have the software on, so I don't know if I showed you or I'll just tell you, but as you prefer. Okay, so basically, when you put your data, you say to the software, okay, the nonlinearity, I want an order 357, and for the low frequency, you have parameters. And so you can try different parameters, and the software will try to fit the best model, and actually it computes the normalized mean square error between the simulation and the model to see if it's accurate or not.
Okay, thank you. Because it's very important to have a very good model PA, because to elaborate the PPT, we cannot use measurement because we can try.
Yeah,
So if we have
sometimes.
a very good model of the PA, we can elaborate a very good PPT.
Yes.
So it's interesting. This is another way to model it. Then the architecture you implemented with 8 variable operations. From that slide 46.
Yeah. I know.
For the digital part, so you choose okay, the duty cycle for the input clock frequency, the duty cycle of 25%.
So actually, the input clock frequency of the circuit is a sine wave that goes into a buffer that generates a square signal, and we use this signal to generate our time interleaved clocks. So actually, I have a slide about the time interleaved clocks. Just to go very fast. Sorry. So actually, this is the circuit. So we have our input clocks after the input buffer. And this circuit divide first by 2, again by 2, and then by 4 with a 25% duty cycle. And so at the end, we have our T-phased clocks for the time interleaved architecture to sample the different levels. And actually, so I found this circuit in the literature. So it was, I think, ISSCC from 5 years ago, something like that. But so with this kind of clock, we have a quite long tracking phase. So we have the circuit has the time to reach the signal, and afterwards we have a long holding phase. And during this phase, we are performing the sharing operation to perform the computation.
I imagine that you have a lot of coupling effects with between the digital bar and the analog part.
Yes.
So how did you manage this?
Okay, so for the coupling, so inside the circuit, so we did some decoupling. So with I would say like a mesh decoupling. So we use odd metal layers for the ground and even metal layers for the power supply. And after that, so just the clock generator is not, I would say, close to the input signal, but actually there is, sorry, I'm just it's quick. Actually, so here is the different clocks I showed you, and they are in a distributive tree to activate this switch link. But actually, I think it may be a mistake because they are under the pathways for the ordered level. So I think this would result in a coupling between the clocks that are in vertical and the signal that is in horizontal here. So maybe to improve this, maybe I should have worked on a different topology, the different layouts. So actually it's quite a big vertical layout, and maybe if I try to make it more like a square wave, maybe make it more compact and not have this long element, but actually like, the paths are very long also. So actually, due to time constraints, I couldn't optimize this part of the layout. Maybe the axis not on this side, but on the other side, maybe because the signal here is the input signal, maybe it's stronger, so it will be less impacted by by those clocks. So maybe it's a solution, I would say.
We saw the result on your manuscript on a destined signal at 1.25 gigahertz, that's great. 156 megahertz signal, and so is the same.
Yes.
Did you, just a question, did you test another signal, or why did you keep on?
Okay, so yeah, actually, again, due to constraints on this circuit, so actually it was a very short design phase. And just to say, I couldn't edit without my colleagues that helped me a lot for this circuit. And actually, I found that it's like a standard signal to test. So since we divided our input clock frequency by 8, actually it's as maybe you were not here for Pierre, but it's a coherent frequency of the input signal, and therefore our Walsh coefficients are constant during all the sharing phase. So we actually need just to do one simulation and one coding and one sharing, and know that it will behave the same indefinitely. And so therefore we do have to do a very long simulation time, because with kind of big circuit, the post layout simulation are very long. So actually to do a full post layout, not including I would say just a post layout of each block, I think it lasted around 1 to 2 days. So just to have one result. So I think yeah, that's why I tested just with one signal.
Thank you for that. Just the last question for the future. So thank you. You did a huge work, and it's the first prototype of this Walsh transistor. It's very good, but still there are limitations. The main speed, the noise, the power consumption. So which limitation for you is the most critical? Could be a hard bottleneck for technology. And yeah.
Okay. Limitation for the circuit or for the algorithm? Both. Okay. So actually, we can find, I would say, a limitation that links both of the circuit and the DPD. So to perform the Walsh transform, it's only a power to 2 number of samples. So actually, in the manuscript, like I wrote, that the memory effect we want to compensate has to be a power of 2, which is a big limitation, because like if we are, I would say, not long memory, like a low coefficient memory effect, it's okay to go from 1 to 8, but after 8 it's 16 and go to 64. And I think this might be the limitation, because for the DPD it will increase the power consumption, since we are working on bigger vectors, and maybe most of the coefficient inside will not affect the DPD, but we need to compute them to have the power of 2. So this is the limitation in terms of the DPD, I would say. And since this circuit computes the coefficient for the DPD, therefore it has to be power of 2 again. And I would say that maybe again a power of 2 for this circuit, maybe some coefficient will not be have some information for the memory effect, for example, and maybe it's too much. Maybe we only need lower order memory effects. So I think this is the constraint to link both of those topics. But for this one, yeah, just for the circuit, if you go, okay, so if you go even higher in order, like I said, 16, 32, 64, you will end up with a much more complex circuit also, because here on the rabbits, actually it's quite complex to lay out and to optimize. It's not really optimized because you have very long parallel paths in here. So if you increase the order, you will have again much bigger circuits, so more coupling contribution. You will have more clocks. So I think it would be like, if we want to increase the scale of the circuits, I think it would be kind of difficult layout. And actually, yesterday in the PhD of Pierre, has 64 coefficient, and it's a very complex circuit. And also, for the DPT to be performant, the orthogonality of the base needs to be respected, and if the computations are not well done, you lost the orthogonality, and therefore you had distortions in the algorithm. I think.
Thank you very much. Because as the DPT is as a function to correct non-linearities, yeah, some results, not all, of the loop blocks can be calibrated with the loop
Yes.
correct the PA and some other.
Yes, maybe.
Some are not so. Thank you very much.
Thank you.
Thank you. Ja, thank you, Monsieur Ferdinand. Un grand merci pour la présentation. Ici, un grand merci à François et Nathalie pour l'invitation pour faire de cette journée inquiétante. Je vais continuer en anglais. By the way, another pretty presentation. Very educational. It's lots of information, but that's normal because you're proud of all the work that you have done. The thesis read very well, very information, but that was also difficult because there was a lot of math involved. But at the same time, it's very impressive to see that you have gone so deep in all the mathematics and also managed to make the circuits and that you showed some more measurement results today. So that's very nice. The first question I was maybe I'll go to reverse order. In your conclusion slide, you said on the DPD that you would like to, and that sounds logical, use the DPD during the PA design.
Yes.
And then I was wondering, suppose you would make it yourself. Which specification would be the easiest one to relax? Or in other words, which specification would be the easiest one to compensate the DPD? Would it be A of distortion or A to B of distortion for a memory?
It's quite a tough question. So actually, I think that maybe the first thing that amplifier designers look at, I think it's the AMAN curve. So it's more intuitive because a power amplifier is to give power to your signal, and the phase is just another consequences of this power amplification. So maybe you will try first to look at the AMAN curve, and maybe as a designer, maybe you will try on the design side to go from topology that has a lot of non-linearities, such as a duality power amplifier or envelope tracking amplifier, and maybe as a base, we will start from on the design side. We will try to make a first design, and then we will maybe before going to a post-layout simulation, just for the concept, you will try to apply a DPD to find, okay, how much I can compensate and what's the power consumption of the algorithm that maybe would be used in the measurement. Does this power consumption impact the overall power consumption of the whole system? So yeah, but for the constraint, I think I would say like the AMAN curve in first. For the memory effects, I think it's a bit complicated because so I did simulation with ADS, and there is some behavioral modeling involved to fasten the simulations, and you have different levels of behavioral modeling, and you have they call this small signal memory effect and large signal memory effect. And so actually for the small signals, as I was looking, it was for the high frequency memory effect, so the behavior of the gain along the bandwidth. But for the large signal memory effect, so I think it involves low frequency, but since we are not doing a temperature simulation in ADS, so this simulation is fixed. So I think there's some investigation to do on NDS, but it's also on cadence to see what behavioral modeling they use, or maybe you could use the other software I showed that modeled the low frequency with two-tone simulation.
If you know that there is going to be very long-term memory effects, either from neural or from bias, and so on, how would it change your solution?
Okay, so I think the solution as the DPD algorithm, for example, or the way to design the power amplifier.
Your whole base.
Yeah. Okay, so as I showed earlier, so this algorithm involves a memory polynomial. So actually, it's I think one of the most simplest mathematical model to model a nonlinearity and a memory effect. And if you want to go beyond to model, to inverse model some long-term memory effect, you might need to go with higher complexity models. I should it's not here, but it's on the slide. Here you have the GMP model, which is I think almost the time used for base stations, because since in base station you have a higher power, high power input, high power amplifier, and therefore there are much more heat. And I think the long-term memory effect might be very significant in a base station. So you might want to adapt the Walsh solution to a GMP model. And I think, and I did some initial tests, it's quite feasible since we know some properties to have the polynomial behavior in the Walsh domain. And with time shifting matrix, we can have the different time shifts of the polynomials also in the Walsh domain. So I think maybe it would be an idea to try to really implement this and see how much we can reduce the complexity of this model. This model has a lot of coefficients and it can go very fast up to 60 and more coefficient, whereas for the MP model that I showed earlier, it was around 10, a bit more coefficients.
A lot of modern communications either make use of beamforming, especially high frequencies.
Yes.
Would it also have an impact on your DPD work?
Yeah, I think so, because since we are sensing the output signal of the power amplifier, therefore there are some disturbance in this output signal. For example, with beamforming, I think that you are modifying the reflective wave, and therefore it will impact the signal, that will degrade your signal. And actually, so in beamforming, you will have multiple lines, so multiple power amplifier and phase shifts to do the beamforming. And I saw in the literature some model that couples the signal from each path of the power amplifier. So the model, so for example, the model will have X from one path of the beamforming and this one for another path. So this model can, so another model which combine both can model how path interacts between each other and maybe how the antenna impacts each other. But I didn't go into this.
If you go back a few slides, on slide 31, but also a few others.
41?
31.
41. Okay.
Because I agree with comment earlier that this is not maybe a fair comparison, because the question is what would it take to go to minus 52 dBc ACPR without DPD? Is that even possible? Did you check if it's possible?
I did not check if it's possible, but I think where you're in the linear state, you don't have spectral recursive, therefore you will have like 60 or 50 dB per but around your channel of communication. I don't know if it's
because I was also wondering, let's go all the way into backup.
Yes.
But then you made the suggestion that actually in backup it gets worse. If you look at the upper right figure in black.
Yes.
I try to understand why there's so much, or why there's such a big cloud. Is this because of noise? Is this memory effect? Or is it just bandwidth limitation?
Okay, so this cloud of dots, so it's due to the high frequency, high frequency memory effect, because on 100 megahertz bandwidth, the gain of your parameter is not flat. So therefore, you will have, if you look at all the ALAM curve along the bandwidth, you will see that it's not superposition.
If it's a bandwidth node, it's linear, and it doesn't depend on the power.
Yeah,
Still, I see that
for the memory effect.
If you go to higher power.
Yeah. Okay. So yes, actually. So I think for the bandwidth. So yeah, I see what you mean. So in those models, there are not, I think, some low frequency, low long-term memory involved, because maybe also the models are used, maybe the models from the PDK in Cadence, they don't model this kind of phenomenon. But I've attended some presentation in which this cloud of dots is very big, also in the known state. So yeah, I can't recall exactly what was your question at the beginning, but yeah. So your question was maybe.
But my feeling is why do things seem to improve by just looking at the black curve?
Yes.
I know this is not true. Things seem to improve with high power. So that would mean that on the left, the fact that you have the cloud is noise-based, because the thing that improves goes to the right as a noise.
Yes.
And then it is noise-based, it is noise from PA or noise from measurement setup.
So actually, maybe it's more proven on the simulation, the measurement. So yeah, actually, in the measurement, we'll see that we have a big cloud of dots that we were able to also reduce the ACPR. And actually, so I will need to do further testing, but the USP I showed, so to generate and send the signal, are not very suitable for DPD, because we use the RX path of the USAP to send the output of the power amplifier, but the feedback doesn't have the same constraints as a receiver.
Because how do you do then? How do you change the input power using USRP? Is it just scaling digital codes, or is it VGA again?
It's yeah. So actually, you can do it by changing the scale in digital. So if you want to have the whole dynamic range of your digital to analog converter, your signal has to be between +1 and -1. And you in the recipe you have a parameter that you can change, and this parameter changes the attenuator inside the USAP. And so actually when it's generated, so it's like at full power of the USAP, and after there's an attenuator to limit the power. And so this attenuator, I think, might induce some noise, like I would say, like, for example, for this power amplifier, it has a very high gain. I think it's around 32 dB gain. So we had to limit the maximum the output power of the USRP, and therefore the signal was in the SLR was not very high. And after that, we had to put some attenuators. So a coupler first, and then I think it was around -20 to -40 dB attenuation after the power amplifier, because the receiver of the US, its maximum input power is -50 dB, and we were like touching the maximum power of the receiver, and I think that's why you still have some issues here. Like we have still some spectral regrowths that may be due to the power amplifier, but to the inside LNA of the feedback path. And actually, also what we can see here on the left is actually the bandpass feature of the USRP, and the noise flow is basically around here. So
industry, definitely, if you talk about telecommunication below 7 gigahertz, 4K1, 4096 QN, which is quite a lot more than the 64.
yeah.
Which also creates a lot of problems just to measure it. I mean, it's very difficult to find measurement equipment that measure 4K1. What do you, of course, you would use these techniques to to amplify the sort of 4K quantum thing? What is going to be the biggest challenge?
I think the biggest challenge is the peak-to-average power ratio. I think we'll have a high peak-to-average power ratio. And I use actually a trace factor reductor in all the simulation to reduce the peak-to-average power ratio, because it was at the origin about 11 to 12 dB peak-to-average power ratio. So with this kind of value, we need to be at high backoff. Otherwise, we would end up in saturation, and we can't linearize saturation. So I think that we need CFR to reduce the peak-to-average power ratio, but actually applying a CFR degrades at the origin the EVM of your constellation. So I think that's why we have some, like it's not up to 0 here or for the simulation, because we applied a CFR that degrades. I don't have the value in mind, but I think they are in the script, the original EVM at the input of the power amplifier. And since this is our reference signal, we can't go below this value. And for 4K constellation, the EVM restriction is very limited. So we can't apply, I think, CFR with 4K constellation. And if we can't apply a CFR, we'll have big PAPR, and therefore we need to be at high backoff and therefore low efficiency.
It's correct to say that with 64 QN, you're still in the AC target? Or that's the
no, I don't think that the constellation actually limits the ACPR requirements. Because so you have your constellation, but after that you'll have all the communication technique like FDM or things like that will actually be more involved in this peak-to-average power ratio. For example, in FDM, if you are all the phases aligned, you will have this peak, very high peak. So,
okay. So, can you go back to the 4 slides? Slide 20, totally Okay, so there is power consumption here, and I think overall, the power that you earn in your DVD is on the low side. If I compare that, which is good, then
yes.
If I compare with the power that you potentially save in a power amplifier, especially if you go to 30 dBm and so on. So I'm not saying that this becomes illegible, but I was wondering, like, how did you put a number of power consumption here? I guess there is some technology. Is this 40 and also 28, or is it different?
So actually, I did this metric because I think people are more I don't know how to say, but power consumption is quite a physical metric. It's actually how much your device will consume. So this was just to give an order, and actually I took energy efficiency of what could be an ASIC, for example, but I didn't try to find what technology uses this ASIC. I'm not sure I can find. So it's a market ASIC dedicated for AI, and we have some partners at K11 that uses this energy efficiency target to measure. But I would say it's a very coarse estimation, because doing a DPD doesn't just not involve the power consumption of the algorithm, but since you need to sense for 3 to 5 times the bandwidth of your power amplifier to sense for the nonlinearities, you need to increase the bandwidth of your converters. So this will increase the efficiency of the power consumption. Same for the digital to analog on both. So you will have these constraints. So this is just to have a more intuitive metric and see, like, if we had an ASIC with such energy efficiency, how far can we go in number of coefficients to inverse our model?
Okay, but if you use a more advanced technology, more scale technology, you go to 7 nanometers, something, these numbers will go down.
Yeah.
And then slide 26. Yes, 505 hours.
Yes.
How do you know this?
Because it was actually a simulation that we wanted. No, actually, we didn't wait, but actually, so it's a simulation of full 5G signals, or 10 milliseconds on sub-terahertz per amplifier at 150 gigahertz, designed by Antoine just here. And so it's post-layout simulation, and since there are a lot of parasitics, and when we tried another transient simulation, at first we didn't solve this number, and after we saw like it will last like almost a month. So, and it's for one iteration, and for DPD you have to do multiple iterations, so you can't wait multiple months to do one digital distortion. So
This number is in circulation, right? So-
no, it's actually what the simulator was writing. But
So we get the simulator in
but-
extrapolation or-
But maybe it would have lasted less, but I think we wait like for 1 or 2 hours. We check at the number, it was still like 500 hours.
Okay. You mentioned AI earlier, right? So a typical question that I now start asking juries is, how did you use AI or GenAI?
Oh, sorry. Yes. Go on.
My question is simply, how did you use AI or GenAI in your research, the thesis, and your presentation?
No, so actually, I talk about AI, but it's actually partners from K11 that. So
No, but just in general, I mean, did you use AI? Could you use AI to find the optimal values?
Okay.
Did you use AI to make that nice figure with the ACPR that increased?
no, actually, so
Wait, so you use AI? It's the same as
so yeah, I think yeah, like as we know, like from 1 to 2 years ago, like, now AI is like everywhere with ChatGPT and so on, and I think it's going closer and closer to the circuit design, and actually it's right here in the telecommunications. So I think this could be so actually, like for example, for my algorithm, I tested different parameters for the model, for the parameters of the algorithm. So maybe we could try to use an AI to like replace me, but he's the one in charge of finding the optimal value. And because I did just a sweep of the values, but it will be further optimized. And maybe in the end, knowing like the behavior of our amplifier, the AI would find the best model for the inverse model. So maybe it could be used for this. And actually, for our side, so our partners from K11 found some digital processing techniques to compute a new kind of constellation with using Walsh coefficients, and actually make sure that it's quite efficient compared to traditional IQ constellation.
Thanks in the presentation. Did you make it?
No,
Not at all.
no. Yes. For the text, I used AI to help me. All the ideas are here, but yeah, I used a bit. But for the slide, I didn't use AI at all. For the animation, it's a sweep of a simulation in ADS, and I just take all the data back and I put.
Yeah.
This kind of stuff.
Slide 14. You made an analogy with people that are wearing.
Yes.
Okay, but glasses, they work on the receive side, correct?
Yes.
Yes. On the transmit side.
No. Yes.
Which makes me wonder, well, can't you just shift everything to the receiver?
Great.
It's a very good reason why you have to do DPD on the transmitter and not at the receiver.
Yeah, I think like on the transmitter side, you know your input signal. I know when you are sending it, so you know because a key constraint about DPD is you have to time align the input and output signal of your power amplifier to build the model. Because if it's not aligned, you will look at the output but the wrong input and vice versa. So,
But are you allowed to transmit garbage?
Yeah.
No, that's the ACPR spec, right? You're not allowed to.
Yeah.
That's the reason why you have to do DPD.
Yes, of course.
Another question I had on this figure, it was also in your thesis. This is not correct. The blue line, the red line, and the...
No, it's not correct, actually.
Because the PA cannot...
It's saturation. It's just an...
So how would the PA line would have to look like?
Actually, it's like this, and then straight...
Or the game is proper.
Yeah, after, yes.
Game
and then it's like this.
technically did correct in your measurements. Where are we now? 5, 6. Slide 12. Almost there. Oh, no, we already covered that. Yeah, that was the same discussion.
Yeah.
We can keep the discussion going during lunch, maybe, or this evening.
Okay.
Slide 10. Well, that's also maybe a detail, but in that definition of PIPR, what is X?
It's the input signal of your power amplifier.
Would that be the voltage or the current? I'm just a circuit designer. I cannot think in terms of signals per bit. So either voltage.
Okay. I think so. Like,
It should be voltage, right?
yeah. Actually, so I did everything around the power amplifier around 50 ohm. So actually, it's in my simulation. I use the voltage from the simulation to compute this picture.
That definition, if I apply the definition of sine wave, I get 3 dB.
Yes, actually, you have.
So
Yeah, because
that's the base
yeah, because it's an because it's IQ signal here, but at the input of the parameter, you actually have one signal, not two. So yeah.
You look at the envelope, you apply that definition in the envelope.
Yeah.
All of the carrier itself.
Yeah.
Okay. Very good to hear that you know what you're talking about. And slide 4. I know. That HV, people have been talking about that for many years. Do you think it will have any point? From an engineering perspective, this is interesting, yeah? They go to high frequencies and so on. You know, I always, this is a very important thing. If you can do it in silicon, do it in silicon. And I think the second statement for me is if you can communicate at a lower frequency, do it at a lower frequency. I'm very skeptical to deploying millimeter wave because you have to do beamforming, lots of drawbacks in the free space bubble and so on. So what's your opinion on this?
Actually, my opinion, maybe on a more, I don't know, not philosophical side, but do we actually need such high data rates for our communication? Maybe I think like what we have now is enough in terms if you want to like see some streaming. So I think like for a kind of application like communication, like everybody does every day, I don't think this is quite relevant. But actually for applications, so I don't know how we do it, but as I showed earlier, for ultra reliable communications, for example, remote surgery, communication needs low latency. But like I said, it's a short range communication. So how can we do it if we want to add a remote surgery on a patient that is all across the world? But this is a small range communication. So I maybe this, for the 5G, maybe it's too high, but right now people are talking about FR3, which might be, I think, in between FR2 and FR1, so maybe it's a good compromise. And yeah, because as you said, there are a lot of technical issues with such
Then maybe a last question, but it might be, it was a figure in your thesis. I'm not sure how difficult it is to pull up your thesis.
I have it. Yeah, I have it here.
There we are. Page 129. Figure 434. Next one. Yeah, this one, of course. All those inductors. Can you comment about that?
Actually,
Are they exactly all nano-Henry? Or what are these inductors? And how do they influence?
okay, so actually, we had some talks with the designers here at the IMS lab, and actually, it's a value we commonly use to model the inductors by the wire bonding of the chip on the package. So that's it's not a constant, and maybe it's not a good value, but actually,
So this is what you simulated. You included those quantiles.
Yes.
Did you have to change something on your circuit after including the quantiles?
So to be truly honest, if I wanted to, I couldn't have the time to change the circuit. But so actually, I think I'm showing here in the following. The computation after the active balance is quite less efficient than after the 3 stage of radix. So, but here it's not actually at the output of the active balloon, it's at the end of this schematic. So it's after this and this. So maybe I could have do some extra simulation to maybe fine tune those values. But also I did some simulation with a high impedance port here. And actually, I couldn't make my measurement works with high impedance because there were a lot of filtering of my signal. Because something that I forgot, I was thinking, okay, my signal, okay, it's this is quite a low frequency signal, but actually you have high frequency transitions to go from a level to another. So actually there are high frequency in this signal, and it's something that I forgot during my design. It has to be taken into account.
Okay, thank you very much. No further questions. Thank you. Doug?
Actually, I have 3 questions for you. So,
Okay.
if you had, congratulations on the research. It's really well
Thank you
done.
very much.
So, I think digital pre-distortion is inherently a holistic or sort of a black box
Yes,
approach
exactly.
to the error, I should say. So, if you consider all of the possible sources of distortion or error in Tau, are there any that cannot be modeled effectively with Volterra series with a sufficiently high number of terms?
Okay, this is quite a lot of questions. So from what I've seen in the literature, the Volterra series, like truncation of Volterra series are used in many cases. And like I showed you the basic GMP, but actually there are lots of GMP models taking into many effects into account. But from the literature, I don't remember any effects that would come from the power amplifier side. I would say maybe from the other chain, because you have the power amplifier, but you still have the digital to analog converter, the mixers, the coupler, and again from the feedback loop. So maybe it's not like one component that we can model, but it's a succession of components since the nonlinearities they progress along the chain, and therefore, if your power amplifier has nonlinearities and your mixer again for the feedback loop, they will be cumulative. And maybe it will be hard to find your model of power amplifier since there are many contributions that I don't have in mind, but I think it's something to
page 37 is section 1.2.3.
Okay, it's loading, I think. Yeah. 1.2. 1.2.3.
It's 1.2.3. Page 37.
Page 37. Yeah.
Yes, 1.2.3.
It's which figure?
Yeah, just right there.
Oh.
So let's look at that first sentence.
This one? Sorry.
There. So
Sorry. I was thinking about the figure. Sorry. Okay.
So, in sort of simple terms, what do you consider the definition of being time variant? What does that mean?
I would say that, yes, it's more like theoretical approaches, but like if we want to model, I don't know, something, filter, anything, it's if we want to see how it behaves, we can use the convolution, and it's usable because we have a linear time invariant system because the system is not changing. I would say the model is fixed.
Right, so what cannot change?
So what?
Something cannot change, so what is it that cannot change for the entire series to be correct?
What cannot change?
Obviously, something cannot be, I mean, by definition, it says invariant. What is it that cannot change for this to apply?
These coefficients can change to
The equation, yeah. Right, so it can be very nonlinear, right?
Yeah.
It can be completely, it's crazy nonlinear. But the nonlinear cannot change over time.
Mm.
It can change maybe slowly,
Yes, slowly.
but it cannot, time variance cannot be a function of signal.
Mm.
So I can think that at least one perhaps nonlinear area that would not pass together since probably is competing. So it's not keeping the device, it's actually keeping the device as a result of the signal.
Yes.
That is not invariant. That's
Okay.
invariant.
Yeah.
So if that's true, then this
Yeah, this doesn't work.
doesn't converge.
Yeah. Yeah.
It can't describe it.
Yeah.
Right,
Yeah.
so let's set that aside. So I think we, now let's turn to Walsh. So can Walsh distortion correct all errors in a power amp, or only those that can be modeled with Volterra series?
Yeah, only those that can be modeled.
You think only those Walsh can be correct, those errors in a power amp,
So
which can be modeled with.
So I think, like in my algorithm, it's the case because I actually take this model and I just do a transfer in the Walsh domain.
All right, so I'm asking you a different question.
Mm.
You've only used errors, you've only used functions to correct errors that can be modeled or by Volterra series. My question is, are those the only errors that could be corrected? Or are there other errors that could be corrected which cannot be modeled using Volterra series?
Yeah, it's
I mean,
no, yeah, it's very, very interesting. So actually, like maybe it could be other because actually the Walsh series are so very suitable for something that is not a linear time invariant system, but a dyadic time invariant system. So a dyadic system would doesn't. Let's say if you have a linear system and a dyadic system, if you send the same instruction to both, you are not applying the same convolution, therefore you will not end up with the same output. So since we know that the arithmetic convolution is often used to model a physical system, maybe the dyadic convolution can be used to model maybe some other kind of system, and maybe those systems have some nonlinearities that the arithmetic convolution cannot deal with.
Answer my question quickly.
Thank you.
Congratulations.
Thank you.
Anything else? That's it for me. If you like an even harder question.
Maybe after.
Thank you very much. I don't have any tougher questions. So I'll try to. So just want first to congratulate you on the presentation. Yeah, I meant like wire segmentation, crystal clear. To me, really great. Thanks for that. I have like first question to understand this pré-distortion with the Walsh platform. Does it apply only to voltage-based DACs, or can it apply to any kind of transceiver that will generate the signal to the bottom side?
Okay. So I think it's more suitable for Walsh-based DACs since we don't need to do an inverse Walsh transform on the pre-distorted signal to use a time DAC. So therefore, we can use the Walsh coefficients. Maybe I have. Yeah, sorry. No, I don't. Yes. Maybe if we go back to the architecture. Yeah, it's at the end. So, okay.
Yes.
So actually, I believe are computing directly the Walsh coefficient of the pre-distorted signal. Therefore, we don't need an inverse Walsh transform here because it's done with the converter designed by Pierre. So actually, it's more suitable since we don't need to do an inverse Walsh transform, so it's less complexity. And on the other side, from this circuit, it's the same way. Like we are directly using the Walsh coefficient of the output, and we don't use the transform in digital. But actually, we can just try to do. I think it's actually what I did in simulation. I didn't put the Pierre circuit in my simulations. Sorry, you would be faster maybe. So, yeah, so, yeah. So actually here it's what I'm doing. So I don't apply the DPD after it's computed on the Walsh coefficient, but I applied it in time domain because I wanted just to test this block. So actually here we have the pre-distortion coefficient in the Walsh domain, and I'm using an inverse Walsh transform on it to apply on the time domain signal. So it could be used just for this adaptive filtering process with its good efficiency, but it could be used in a very conventional transceiver.
Okay. And you did not mention the motivation for the analog Walsh transform because you can use also digital
Yes.
Why would you to go for this analog implementation?
Okay, so from more conceptual or technical aspect, some great ideas we have here in the lab is the concept of a full Walsh transceiver. So the analog Walsh transform is used in the feedback path, but it could also, since it's a feedback, like a receiver, it could maybe be used in a receiver. So this was a motivation just to see if can we do it in analog, and actually it's done in the same way as Pierre, where Pierre is taking the function, he writes them and sum, and you have your signal. Here it's more like the digital computation where you have the levels and you just add additions, subtraction. I think actually. So Pierre's circuit could have been used for the feedback loop, but in another way around. I think maybe we can find something that works, but also the radix circuit could be used in the transmitter side. If you put all the Walsh coefficient in analog and then you sum them, and at the end you put a demultiplexer to reconstruct your time signal maybe. So this is for the concept part. And I had another idea, but I can't recall that.
So there are many ways to implement this receiver and transceiver as well. But my question was more like, what do you gain for going into this analog implementation?
So
Again, I don't know, on the ADC receiver, like a lower range, or
yeah,
what do you gain?
yeah, actually, maybe I will put this. Yeah, so actually, as you mentioned, since we are going to one signal to multiple signal, we are doing power. Therefore, we can reduce the speed of the ADCs. So this is, I think there are many architecture with time interleaved architecture for ADCs. I think there are even some frequencies. Actually, there are some frequency interleaved architecture, and maybe I think it's quite interesting because in Walsh or in Fourier, we can do a very, I think it's easy, it might be easier sometimes in Fourier to do a filtering. And if we can do it in the analog domain, maybe we can use some constraints on the ADCs if you are, as I said, if you have blockers, and maybe you can filter them using those levels. And since, for example, if you take Fourier, you just multiply your Fourier coefficient by the coefficient of your filter. So I think so. Professor Argeni did something like this in a circuit, and I think it's quite easier implementation do some filtering or in Walsh. We could also do it in Walsh rather than in time domain, because I think once you have your level, actually you can maybe have a programmable filter, I would say. Maybe if you use, so I showed earlier charge sharing capacitor to do some additions, but if you change the ratio between the capacitor, you will end up in the weighting of the voltage, so they will not be equally separated, and therefore, actually, it's what's performed with the analog Fourier transform to do the weight in the Fourier transform. So I think it would be an idea to do filtering with this.
And what would be the main problem or challenge to solve for getting to larger event, like to reach 100 or 200 megahertz? So what would be the problem for like 400 megahertz or current aggregation with the algorithms?
So yeah, I think like if you increase the bandwidth, you need to increase the sample rate. Therefore, you increase the power consumption of your circuits. So I think this is the first, main problem. And if you want to have low sample rate here, you will need to have a high number of coefficients because you are dividing the maximum by the number of branches. But if you have a high number of coefficients, you will have a big circuit. If you have a big circuit, you have many sources of parasitics, and therefore its implementation might be difficult.
Okay. Maybe a last question on the second design. So I appreciated the way you have described your sequencing in the manuscript, like each block is separately. So there are a lot of blocks which used to be like a high-speed digital design. And the way you design them, it's more from an RF background. Like each block is situated, and it's really resembling the schematic.
Yeah.
I guess when you look at the final, I mean, you mentioned that in the presentation, you look at the final layout, there's a lot of blank space around, and there's a lot of connections. So it's silicon for connections.
Yeah.
So what would you do differently to for go back to your
okay, so I think like I basically took like the first like draw it like you see it. On this case, actually, if you look at the theoretics, it's exactly like this. And maybe before going to layout, do some drawing, and because there are a lot of signals interconnected here. Therefore, this one was here, but it's actually connected here, but also connected here. And there is like a long connection, and maybe we could try to find actually what levels are connected in between each other, and try to make them like more compact, maybe more like a square block rather than a vertical block. And also I mentioned that Antoine here helped me a lot to do this, because even if it's like draw it like you see it's quite difficult in the end here where you have a lot of interconnections.
Oh, just a curious question. You mentioned you have two blocks.
Yes.
On your layout. So I was wondering how you turn these two different blocks on phase or something like that.
Yeah. Maybe on the layout, so final layout. Yeah. So yeah, actually, so actually, at first I was not planning to have to double this the digital block, and actually inside this block, all the different clocks for all these circuits are computed. But if I take this one and it has to be like up to here, the pass like almost 1 millimeter.
I mean, you
And
have two clocks.
yeah, but so actually, so I was mentioning that this measurement bench needs to be improved, because if we want to have the continuous sampling performing, we need those clocks to be perfectly synchronized, and as we saw, they are very high frequency also. So I think you might need some additional circuitry to do this. And
the two clocks are the two ping-pong paths.
Yes.
Okay. So, non-manageable. Okay. Okay. Thank you very much.
Thank
So
you.
thank you for taking questions.
Thank you very much.
That's it. Yeah. Next, Eric.
Yeah. Okay. So thank you, Mr. President. And first, I would like to say that I'm very proud to be a member of this jury and for the communication, of course. I would congratulate you for quality of the foundation and the use, the excellent use of your slide. It's very didactic and on a convincing way for you developed this Walsh 3D for PA. I would like to slide 12 in my case.
Yeah.
Okay, I have a little story to the audience. I would like to say that we will go to discussion with François in my office here in IMS, and where François was trying to explain how the Walsh console is working, and I suggest him, I would say also that this idea is coming from discussion with Jan and also Doug Smith to talk about more sequences to generate kind of signal. And I'm not sure that I perfectly understood the word transfer. I suggest transfer to use this mathematical pré-distortion or mathematical function for the distortion for the TLA. And we got that a few years ago. This new concept becomes very because we present there very nice work where we can see that this work is working for the denotation. So calculation again for your work. But I'm sure that was possible because we were selected or chosen by François and Nathalie. We are understanding of analog digital and error electronic knowledge, on understanding of digital communication, and your very high level mathematical background makes thesis successful. I'm sure.
Thank you.
I have two short questions. The first one to present the Walsh mathematics and also Adam. And can we say that this proposed technique is able to generate an EDD with this two-way Walsh lemma? And in this case, the same architecture generates the lemma in both equations. So in function of the PA non-linearity, can we choose one set of coefficients, for example, Walsh, or another one, Adama, to correct to linear the PA? And maybe can we switch from one set of coefficients to the other one to improve the performance of your?
Okay, so maybe I can go back to the different ordering. Yeah. So actually, if you look at the Adama order, it's actually the same function as the Walsh function. They are just rearranged in a different order. So basically, at the end, you would end up with, I would say, the same performances. However, the way, for example, this is computed digital is much more efficient than if you do this kind of multiplication. You just a recursive formulas or just the computation of the Walsh matrix, for example. This might be more useful. So it's for the Adama side, and also. So I would say this would be more suitable on the DPD digital side. So we use this computation to create your matrices. And on the circuit side, actually, the analog transform, I've shown you actually the output coefficients are arranged in an Hadamard order. And we just need to just inverse some coefficient to get actually the Walsh coefficients. But I would say in the fast Walsh transform, if you want to have an Hadamard order here, you will have successive data like a time successive. And if you want to do a Walsh order here, you will need, I think here it would not be like x1, but x4, for example, x3, sorry. And here it will be different. And actually, I use this architecture because the consecutive, the signal in the first stage are just one after another. And on the circuit side, I think like in my track and hold circuit, each track and hold generates a very, I would say, I don't know how to say, but in this order, the levels we get for the Walsh transform. And if for the circuit we wanted to do an Walsh ordering, it would have changed many things in the circuit, in the interconnections. So maybe also there is a better interconnections for Hadamard order, maybe. And actually, yeah, I choose this one because since like I said earlier, it's a draw it like you see it, and it was the follow the successive samples here. So in the circuit, you get the successive samples. But if you want to combine x0 and x4 on the circuit side, they will be very far from each other, and therefore there will be a longer path to access the transform. I don't know if it was.
The last question is about the parameters in your T on the classical T. In terms of frequency range, do you think that it's possible to address all the frequency bands of the 5G example in FM2 and FM3? And is only one TV circuit, or we need more than one circuit to address that?
Yeah, so I think maybe you might need one for FR1 and maybe one or two for FR2, maybe one. But actually, yeah, like on the I would say the frequency is just a variable for the computation. So this kind of architecture does not depend on frequency, but frequency will impact the rest of, for example, the circuit, the power consumption will be increased. So and maybe you could also use it, but at lower frequency. For example, maybe you could go from RF to baseband, and you will have less constraint on the circuit. So yeah, I think it's much. The algorithm is not frequency dependent, but the overall system is frequency dependent.
Yes. Okay. So a last comment. I think that it will pave the way for other works, of course, based on the use of the Walsh frequencies and the Walsh transform, the Walsh limit, or Walsh Hadamard mathematics. So I would like to say that we are a student from some mathematics. I'm very proud of mathematics, that's why I'm very proud of that. And congratulations again, and thank you.
Thank you very much.
Désolé, oui, ça change. Une présentation exceptionnelle, vraiment, qui, j'en suis pas surpris, a réussi à marier la rigueur et l'esthétique. Alors, vraiment,
merci.
Je ne vais pas m'attarder, vous savez tout bien, je pense, de votre travail, etc. Mais là, comme pour Pierre et tous les membres de l'équipe, une super ambiance humaine, voilà, avec un soutien les uns envers les autres. Allez pour ça, merci.
Merci beaucoup.
Yeah, thank you, Mr.
are used to see you presenting excellent slide and the way you present it's perfect. But also thank you for the quality of your manuscript. It's very well written. Of course, it's difficult because it's a lot of mathematics and it's quite high level. So you were the perfect guy for what we now call design by mathematics. You perfectly with that. And you did an excellent job, which is you just work on big plans, right? And also this analog watch transform the butterfly algorithms, which remind what the work we have done previously with, let's say, Fourier, now it's Walsh, so the SAS François and a Walsh generator. That's really great to see that how it works nowadays, how it performs, and how it progresses, and how it opens also a lot of ways in terms of DPD, self-fitting DPD as well, with other functions that there are. It's really opened the way to so many work and thesis. Thank you so much for having been this pioneer and excellent work here. We have met at least in 3 years, so I will have no other question because I know your work and how you progress. I have no special question, but I would like to thank you so much for what you have done and to congratulate you for all the work, the quality, the quantity, and the way it was presented. Thank you so much.
Thank you very much.
Thank you. I guess I'm next. I have just two questions. One is the Hadron sequence is used in a number of other applications, like parallel thinking, schema development, parallel. What other cases in your reading did you find that it's being used?
Okay, so
outside of this.
So I think I saw we know orthogonal frequency division multiplexing. I think there are quite some work about orthogonal Walsh division multiplexing or Adamo division multiplexing. So maybe it might be useful to use it maybe to see its advantages over OFDM. I don't know if it might be. I think there are some more, but I don't know actually what's inside. And also in what I've seen is that so I showed that we can do filtering with Walsh, and maybe okay, let's say that I showed the filtering matrix, so it's actually a block diagonal matrix. But if you want to do in Fourier, it's actually just a pointwise multiplications. So maybe you could say, okay, it's not very. It would be more complex to go in the Walsh domain to do the filtering. But actually, if we look at the transform, it's much more efficient than Fourier transform since it's only additions and subtractions. And there are not any multiplications involved, and there are not weighting in this transform. So I think being the filter aside, just putting your signal into the correct basis, it has to be taken into account. And also, I've seen in the literature that if your filter in time domain has some symmetrical properties, the filtering in Walsh will be, for example, anti-symmetrical and purely real coefficient and not complex. Therefore, complex multiplication is like a 6 floating-point operation, whereas if it's real, it's only 2. So I think it's a great tool to do some filtering.
Thank you. And the last question, leakage compensation. Can you explain that a little bit?
Okay. Yeah, maybe a bit long. Okay. So actually, I choose this topology. I think it's quite a famous one. Maybe not in a CMOS switch, but I've seen it a lot, and I think it's the switch you are using in the analog for you, the charge use analog for your transform. And so here you have the switch that performs the track and hold. On the side, I added a dummy switch to help evacuate the charges when the clocks goes from on to off. And when this switch is off, it's actually not entirely off. There is some leakage in between. And since we're working with the differential signal, here you will have the same signal in opposite phase if it's 180 degrees. Therefore, if we have the same leakage here, this is used to re-inject the negative leakage to the opposite and the other side, and this will, I think, that's what helps the isolation of this switch, for example.
And did you use a constant BGS sample
Sorry?
for your input track? Did you use a constant BGS sample?
Yes, it's constant.
That's all the questions. Thank you. And that's it.
Thank you, Mr. President. So I would like first to thank Étude and Patrick for the two reviewers and all the jury members for agreeing to participate to this event, for the question and the comments, and Étude to highlight the work you've done and to give you the opportunity to show the excellent work and the extent of your skills. So you have clearly exposed the contribution to this thesis work, and it was a real pleasure to work with you, to work with such a willing person, with a lot of proposition, always ready to take on challenges, even when it was complex, and even when it was not planned at the beginning of the thesis. So we start with you mathematical development of DPD based on Walsh theory, development of simulation methods for DPD with a homemade tool and the evaluation of the vision tool with Ampere. It was really important to work on this because it is important to work on DPD, but it is also important to take into account the PA that you want to realize. We also worked the implementation of different linearization benches that you mentioned. Analog work from your side. All this required a lot of work and tenacity. I want to say that, okay, I want also to highlight your ability to make wonderful slides with animation and illustration that make it very easy to understand, quite complicated concepts, even if when you come deep to mathematical complex, it is always very hard to follow. I also wanted to thank you for the participation in the workshop of the joint ST and IMS laboratory, and remind that the project you were involved, Aggregate 5 and IMS, were in the frame of this joint laboratory. And I just want to say a few words in French. Donc, merci pour cette présentation du travail réalisé. Donc, nous avons commencé la collaboration par un stage, je précise, dans l'équipe CSH. Donc, ce stage, l'objectif était de commencer à travailler sur la mise en œuvre de cette DVD. Tu nous avais indiqué à l'époque que le sujet t'intéressait beaucoup, mais tu ne ferais pas la thèse après, tu avais d'autres projets.
Je me souviens plus vraiment.
Tu m'avais dit, je fais le stage, mais je ne resterai pas après.
Je suis pas prise. Oui, je me souviens.
Et finalement, je crois que tu t'es vraiment épanoui dans l'environnement, parce qu'il y avait le sujet, il y avait aussi en groupe de personnes qui travaillaient sur les projets avec toi. Tu as parlé beaucoup de Rémi, d'Antoine, il y a également Pierre. Donc, dans cet écosystème-là, qu'on a pu mettre en place, tu as bien pu t'épanouir et je suis vraiment ravie que tu sois resté, parce que tu étais la personne clé pour réaliser ce travail. Effectivement, sur les différentes approches que tu peux avoir, et la compréhension fine que tu peux avoir, aussi bien des mathématiques que du circuit. Et on voit bien à travers la réponse aux questions ouais, tu te poses les bonnes questions, des fois c'est pas sans y répondre, mais en tout cas elles sont posées et on voit que tu as toujours une bonne réflexion, un bon niveau de réflexion à poser sur les différents points de travail. Alors c'était un peu plaisir de t'encadrer, tu es sérieux, ça c'est rien de le dire, tu es rigoureux, c'est aussi quelque chose qui te caractérise, tu es autonome, tu es curieux, tu es vraiment curieux de beaucoup de choses et c'est ça qui était très intéressant pour nous, toujours à l'écoute de nos recommandations et de nos propositions, ce qui est vraiment très appréciable pour un encadrement. Là, quand on peut discuter avec toi et qu'on peut poser quelque part un défi, tu le relevais systématiquement et tu t'intéressais vraiment à ce qu'on pouvait proposer. C'est toujours. Donc, j'ai parlé un peu des doctorants qui étaient autour de toi, donc avec qui tu as vraiment collaboré. Et puis, sur le TEPA, tu l'as indiqué, tu as eu tout le temps, il y a beaucoup de gens aussi qui ont pu t'aider, vous avez travaillé en groupe, c'était vraiment, tu as aussi su, profiter de tout cet environnement-là et su créer aussi autour de toi cet environnement. Et c'est vrai qu'on a quand même beaucoup de chance, en tout cas, moi j'ai beaucoup apprécié pouvoir travailler dans ces conditions-là et voir l'entraide entre vous, la solidarité entre vous qui était vraiment très forte et c'était assez touchant finalement. Alors je souhaite bien sûr que tu t'épanouisses dans tes prochaines aventures, dans tes prochains défis et que nous pourrons continuer à travailler ensemble sur des projets, c'est bien évidemment tout à fait possible. Je voudrais aussi remercier mes collègues qui ont participé à ce projet et à ce travail, et particulièrement François, puisqu'on a co-organisé ensemble plus particulièrement la thèse. Je vous remercie pour sa confiance. J'ai beaucoup apprécié de travailler avec lui. Et donc cette collaboration continue. On a encore des thésards en cours, Camille, Antoine, Pedro, et puis peut-être d'autres à venir. C'était vraiment un plaisir. Alors, de t'encadrer, bien évidemment, tant que tes qualités sont évidentes, et également de travailler avec François dans le cadre de cette collaboration, et travailler avec mes collègues dans le cadre des projets Hermès. Merci.
Merci, Monsieur le Président. First, we would like to thank all the jury members for being here today. My gratitude first goes to my dear friend Ramesh, who accepted to be the president of this jury. So, Monsieur le Président. And everyone knows that being president in France those days is torture. Thank you, Duke, Dr. Wall from Austin, Patrick from Leuven in Belgium, and to Patricia and Antoine from Paris and Lille in Chile. Thank you for joining us. What a pleasure to finish the year with you all. Yesterday and today can be seen as a scientific exploration of Walsh theory in RF communication, circuit and system. Like I said yesterday, it's a single cone with two sides, circuit and system. Yesterday we were circuits, today we focus on the system. So yesterday I said the story of this concept, which began in 2011 with Andela and Smith. Today it's part 2 of the story. So a few months after 2011, when we initiated that, I remember when introducing the concept in a meeting room called Annex B to Eric Garave, saying that we could perform back then software we would like thanks to Walsh. And he answered that he would be happy to watch several sports channels at the same time. That was the machine, in fact. And it was quite true that Walsh is a game changer. And that's why I said that the Pandora box, I would say no, the Walsh box was opened thanks to Duke. And it took me years to come to that simple definition of Walsh. The sequentielle domain captures characteristics across multiple temporal and frequency scales within a single set of coefficients. It offers efficient signal processing with both diversity for error signal and sparsity for computation. And this is what we demonstrate today. So Eric came back into the game, well, several years after, in 2016, I think, when we were at the door of your office, and you asked me if Walsh was performing spectrum sensing. Sure. Yeah. And I asked you what for. That if you can do it, you have a DP. And this is where we started that discussion, and we drew the schematic of the Walsh DP on your wall. And went in the office and we do it, maybe sit there. And in a few minutes, with the right question, it paved the way for a proper answer that took years to demonstrate. Then we have the opportunity of COVID that gives me the time to review the literature. Thanks to Doug, who left me a folder full of papers in 2016. I had time to think about it, and that was a starting point for us. This is how came the Liebig convolution and the Hilbert training. So Jan, Eric, Nathalie, Hervé, and I will form a team to apply for funding and only to hire young, promising engineers. Et comme je le disais hier, certains se rappellent encore du moment où on est notifié que le projet était accepté en cours. J'ai un peu crié à ce moment-là, ou en réunion, aussi où je ne revenais pas. J'ai demandé confirmation qu'on avait bien été accepté pour ce projet européen. On a donc recruté et on a eu la chance encore d'avoir les bonnes personnes au bon endroit, au bon moment. Rémi, Antoine et vous, Maxime. Alors, Rémi et Maxime ont fait leur stage de master. Bien sûr, je précise que Rémi a fait son stage dans l'équipe CAS. Faire à souder à la main, faire la première démonstration de la conversion de Walsh, qui a conclu que seule l'intégration d'un circuit peut bien faire les choses. Très belle conclusion. Et avec Nathalie, que je remercie vraiment, car elle a marié nos expertises, et j'irais même au format d'âme. Depuis, on propose alors le tir croisé, à savoir que dans les petits mercato, Rémi part en CSH, d'arriver en CAS, pour faire vos thèses sur le même projet. Un pour l'amplificateur de puissance, l'autre pour la pré-distorsion. L'un ne va pas sans l'autre, c'est valable pour le PA et la TPD, mais c'est aussi valable pour Rémi et Max Rand dans la vie de tous les jours. C'est un système complexe. Donc, par exemple, on va alors commencer à travailler sur la DPD, puis Walsh, puis la DPD de Walsh. Avec ce moment, on a dit, Maxence nous parle de convolution diadique, c'est quoi ça? Et là, j'ai compris qu'on s'était compris. Pour moi, l'aventure commençait. Alors, Maxence, je tiens à vous remercier chaleureusement pour cette année d'investigation sur Walsh. Vous avez été au fond des choses, mais alors de toutes les choses, une théorie très, très détaillée, des algorithmes très, très détaillés, des simulations, un simulateur, des algorithmes simulés dans votre simulateur et sur des radiologiciels, un circuit qui prépare ces algorithmes, utilisant la théorie, et vous y allez passer des nuits, il faut le rappeler, pour elle, le premier de l'ange, pour concevoir ce circuit avec vos camarades de jeu, et je veux dire peut-être de souffrance. Rémi, Antoine, Pierre. Bref, je pourrais dire que certaines auraient pu s'appeler 50 nuances de DPD par Maxime Feldman. Vous avez dépassé le système de DPD. Vous avez optimisé toujours plus et plus loin. Si je dois vous qualifier, vous avez une réflexion en profondeur des choses avec un goût du résultat qui est comme celui de votre DPD, le meilleur possible, même s'il faut tirer. Par exemple, au side, pour arriver à un qui peut tendre à la perfection. Vous avez donné une autre dimension à l'utilisation de Walsh dans les systèmes RF, justifiant parfaitement ses propriétés de diversité et de parcimonie. On était même au de l'hyper. Il fallait s'accrocher, que c'est anticausal, on déplace ARP. On sent bien que Walsh n'a pas encore fini de nous inspirer pour pousser les limites de la recherche en électronique. Alors, je vous remercie sincèrement pour ces années de travail très denses, très intenses, avec un résultat qui ne peut que vous satisfaire et dont vous pouvez être fiers. Je vous remercie également pour toutes les discussions de très haut niveau que nous avons eues dans notre domaine de recherche. Je vous félicite vraiment. C'est excellent. Je vous souhaite une épanouissante continuation à votre vie professionnelle et personnelle. Merci.
Merci.
François et moi, on a passé du temps à se demander si vous alliez tomber. Il y avait des moments où vous aviez le pied comme ça.
Merci beaucoup.
Mais moi, j'ai compris ici.
L'animation.
Oui, voilà, il y a
The jury agreed for PhD. Congratulations. Take a few more moments to add the feedback provided. First was on the presentation. It's excellent amount of work that you've done, both in terms of being extremely educational, in educating a really varied sense of topics. You worked on developing a basis for the Walsh transform. And actually, I have seen the Hadamard transform probably 20 years ago, but this is the first time I've understood between yesterday and today how it actually works. So thank you both for you and Kim. And I think I want to personally also add this is the way you, obviously, people come from signal processing background, people from circuits background, you're able to cross that boundary. And you should be very proud of that. That's something that's very unusual. The cross-disciplinary nature of that. On the presentation, one negative, went too fast. But just the way you covered the material and what you cared across is very, very positive. Also, the way you answered questions clearly showed that you have a lot of knowledge in the subject, and also want to add to the fact that when you found that it was outside your expertise or it was beyond your expertise, you were very honest to say so. That honesty is very important in technical knowledge. So I want to congratulate you on that as well. With that, I think that's the kind of feedback I have. And then you have to agree. So you can or not agree. So in the presence of completing your doctorate, you have to take a set of oaths. I have to read it.
Yeah, that's almost ready.
Okay.
That's just-
All right. We propose you for the PhD degree of the University of Bordeaux in electronics. Congratulations for that.
So, en présence de mes pairs, parvenu à l'issue de mon doctorat en électronique et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et résultats.
Thank you. Thank you, everybody, for being here. Okay.
Okay, so just a few words first in English. First, I would like to thank you, all the members of the jury, to have read my manuscript, and maybe if it was hard, so something. But thank you very much for the reviewers, so Degas and Professor Reynald for your reviews. It was I was very happy when I got them, and thank you very much for all the members of the jury for your very interesting questions and thoughts around this topic. We'll go French. D'abord, j'aimerais remercier les encadrants, François, encadrant principal de CAS, et Nathalie pour leur soutien de ces 3 années et demie contre le stage. Je n'ai pas vraiment les mots, mais je dirais que vous m'avez donné l'opportunité d'être libre et de lancer sur ce sujet et d'être complètement, on va dire, libre du chemin où j'allais. Mais vous m'avez quand même aidé le long du chemin pour choisir le bon chemin. Là. Et je vous remercie beaucoup pour ça et aussi surtout pour ces derniers mois qui étaient assez durs sur la rédaction. Désolé. Et surtout sur vos conseils sur le manuscrit, sur les slides. Pas en faire trop, de s'arrêter un moment. Je sais que j'ai du mal, c'est mon problème. Je travaille sur ça. Et voilà, merci encore. Je voudrais aussi remercier les autres encadrants côté CAS qui ont été là tous les mois, toutes les semaines à faire nos réunions hebdomadaires, bien énervés pour le circuit, pour les concepts mathématiques aussi. Je pense que c'est aussi grâce à ça que tu peux arriver à ce travail à la fin. Et donc, merci beaucoup. Et maintenant, je voudrais passer du côté de mes collègues au laboratoire. Donc, collègues et amis, surtout, merci beaucoup d'avoir été là. Je pense que ce travail est grâce à vous. Que ce soit plus les interactions qu'on a tous les jours, ou sur le circuit où vraiment je ne pourrais jamais vous remercier assez. On n'a pas assez mentionné Maxime, mais merci Maxime, parce qu'en fait, on était sur le même circuit. Donc, on a un circuit commun où nos puces sont dedans. Une puce commune où nos circuits sont dedans, plutôt. Donc, merci encore. Je ne vais pas m'étaler plus longtemps, mais moi, je voudrais passer du côté de ma famille. Je voudrais remercier mes parents de m'avoir accompagné depuis le départ. C'est qu'au lycée, je n'étais pas forcément quelqu'un qui bossait beaucoup. Et c'est mon père qui m'a un peu, à dire, chamboulé. Et ma mère et mes soeurs qui ont toujours été là pour m'accompagner. Merci encore. Et aussi toute ma famille qui ne peut pas être là. J'ai du mal à prononcer. Léa qui était là avec moi pendant cette 3 ans de thèse. Et sans elle, j'aurais clairement pas pu vous présenter ça. Donc c'est vraiment grâce à elle. Voilà, merci. Désolé pour les... Voilà. Merci. Ah oui, il y a un peu, je pense à partir de 17h, donc vous êtes tous conviés au cours. Oui, c'est vrai que je n'ai pas forcément mentionné. Donc il y aura un peu vers 17h, on est à la cafétéria du laboratoire IMS. Donc j'espère que vous viendrez nombreux pour discuter. Merci.
C'est